Welcome to discussion 8. In today's discussion, we'll be focusing on section 2.5 on continuity and 2.6 on infinite limits. In this video, we'll do some examples where we see if we can make a function continuous by defining its value at a particular point. So let's begin by recalling f is continuous at x equals a if the limit as x approaches a of f of x equals f of a. So that limit needs to exist and it needs to be equal to the value of the function f at x equals a. Equivalently, I could break down this limit into its left and right-handed limits and say that I need the limit as x approaches a from the left of f of x to be equal to the limit as x approaches a from the right of f of x, and both of those need to be equal to f of a. All right, let's look at some practice problems. So this is from worksheet 4, problem number 2, and it says, if possible, define a value at x equals 0 that would make the function continuous. So I want to begin by giving you 5 minutes to try this problem. If you get done with part A in those 5 minutes, then move on to part B. 4, 3, 2, 1, pause the video, pause it for 5 minutes to try this question. All right, so hopefully you did that. Hopefully you paused it for about 5 minutes to try this. Let's talk about it together. So the first thing that I want to check is with f, well, what happens if I just plug 0 in? Because if 0 was in the domain of this function, because this is a rational function, it's a polynomial divided by a polynomial, anything that's in the domain will be a place where this is continuous. But if I do plug 0 into this, I get 0 on the top and 0 on the bottom, and the 0 on the bottom is a problem because that makes my fraction undefined. Okay, so for f to be continuous at x equals 0, we need, and I'm going to rely on our definition of continuity that we recalled above, we would need f of 0 to be equal to the limit as x approaches 0 of f of x. So my idea is going to be, let's find this limit, and if that limit is a finite number, that is what we're going to set f of 0 to be equal to. All right, so let's write this limit. Limit as x approaches 0 of x squared minus 4x over x. We already know what happens if we plug in. We get 0 over 0, which is an indeterminate form, so we'd have to simplify. So we get the limit as x approaches 0. I could factor an x out of the top to get x times x minus 4, and then over that x on the denominator. Now I can cancel the x's, and after I cancel them, now I can plug in. And plugging in, we are going to get 0 minus 4, which is negative 4. So thus, to make our function continuous, we are going to, let me write that better. Thus, let's define f of 0 to be equal to negative 4. If we do that, f, our function, f is going to be continuous at x equals 0. All right, now let's look at part B. It's got a similar function, but the powers are a little bit different. Okay, so g of x is x minus 4 over x squared. For that function, if I do the same thing initially, if I plug in 0, I'm going to get a negative 4 in the numerator, 0 in the denominator, so this is still undefined. Okay, so let's proceed in the same sort of way. For g to be continuous at x equals 0, we would need g of 0 to be equal to the limit as x approaches 0 of g of x. All right, so we're going to find this limit as x approaches 0 of our function. And if that's a finite number, that's what we'll set g of 0 to be equal to. All right, so let's take this limit. The limit as x approaches 0 of g, let's write what g of x is. My function was, it was x minus 4 over x squared. And I know that when we plug into this function, we get -4 on the top and we get a 0 on the bottom. So we have a non-zero on the top and a 0 on the bottom. Recall that our strategy for these is we would use one-sided limits for a non-zero on the top and a 0 on the bottom. And we've seen before that when we do that for a non-zero over a 0, this will be either positive or negative infinity. If from both sides it was positive infinity, it would be positive infinity. If from both sides it's negative infinity, then the whole thing is negative infinity. Or if it's different from the two sides, it would be d and e. Those are the only possibilities. But g of 0, when I plug in a number into my function, I can't get an output of infinity or negative infinity, and I don't want g of 0 to be undefined. We need g of 0. We need it to be finite. Okay, so when we took this limit, it's either going to be plus or minus infinity or d and e, but g of 0 must be finite. So it's impossible. It is impossible to make g, our function g, continuous at x equals 0. So just talking about this graphically to end the video, in part A, we had a situation where when we tried to plug 0 in for x, our function was undefined, but the limit was equal to -4. So what that meant graphically was, if I labeled -4 on the y-axis, our graph did something where it got really, really close to this y value of -4 as x got close to 0. But because it was undefined there ended up being a hole. And because there's a hole like this, I could just fill in that hole. I could make a g of 0 be equal to -4, and that would make my function be continuous. Okay, in part B, with this graph, at 0, so when x is 0, we said that we needed to take one-sided limits. We didn't actually do them because we realized, oh, they're either going to be positive infinity from both sides or negative infinity from both sides, or maybe one's positive and one's negative, and that would make the overall limit be d and e. It turns out that if you do take those one-sided limits, both of them end up going to negative infinity. Turns out we have a situation like this. They both end up going to negative infinity. And if I have a situation like that, there's nowhere I could just put a point and define g of 0 to be equal to something that would make this be continuous. Whereas with part A, I can. I would define f of 0 to be -4. That would make it continuous there.